Hello, today we're going to have a look at the category of affine schemes and we'll see how it's related to the category of rings. And in fact, we'll see that it's equivalent to this category. We start with defining a functor from the category of rings. We will call it Spec as the spectrum as we already had for this functor from rings to topological spaces, but now it goes into affine schemes. Okay, it's quite clear what it should do. On objects, so a ring A just gets mapped to an affine scheme. So of course we view the spectrum now as a locally ringed space, so not just a topological space, but locally ringed space and therefore as an affine scheme. Okay, the next thing we have to do is we have to see what this functor should do on morphisms. So let's take a ring homomorphism from A to B. And now we need a morphism of affine schemes. So this is such a tuple, such a pair from XOX to Y in the structure sheaf of Y. And of course, Y is the spectrum of A and X is the spectrum of B, and F is just the spectrum of phi, so now viewed as a functor into topological spaces. So this is the map on topological spaces. And I'm not going to be 100% consistently, so sometimes Spec will denote the functor into affine schemes, and here it's the functor into topological spaces, but it should be clear from the context what is meant. And similarly for another notation I'll introduce soon, but now let's see. So we need this F and FB, and F is already given. So what we really need is this FB from the structure sheaf of Y into the direct image of the structure sheaf on X, or equivalently we can we've seen previously that we can use the inverse image of the structure sheaf of Y into the structure sheaf of X. And what I already mentioned before, we introduced some notation, so we'll write instead of spectrum of phi, so just as a phi. And this is for both, so for the functors into affine schemes and also for the functor into topological spaces. Okay, and now we have to define this FP, so let's do it. We define it just on the basis of principal open subsets, so that's enough. So let's have a look. What's OY of D of S? So that's just the localization at S. And we need a morphism into the direct image OX of D of S. And now let's see what the right hand side is. So D S. So that's just by definition x of the inverse image of d of s. Now f was defined as the spectrum of phi, so that's just the inverse image under the spectrum of phi, and you can easily show that that's just Ox of d of phi of s, and well, that's easy now. This is the localization at the element phi of s. Okay, so that's what we need. So we haven't defined it yet, but just to see what we actually need. And so we have these morphisms here, and by the universal property of the localization we get a unique morphism here, and that's just the definition of fb d of s. Okay, so now we've defined that. So that's good, because now we have a morphism of ringed spaces, and we'd soon check that it's a morphism of locally ringed spaces. But first, let me give a short remark. So if we look at d of 1, then we have a y of d of 1, that's just a into b, and this map is in fact just phi. And this already gives us a hint. So later we want a morphism, a functor in the other direction, so from affine schemes into rings, and this gives us a hint for later what it could be. Okay, so as I've already mentioned, we have a morphism of ringed spaces. Now we check that it's a morphism of locally ringed spaces. Sorry, let me one step ahead. So we have to consider the morphism on the stalks. So from Oy f of x into Oxx, and that's just a phi inverse of px. So px is the prime ideal corresponding to x. So that's, let me make it more clearly. So that's the localization at this prime, and here we have the localization at the prime pi x. Okay, now let's draw a diagram. So we have morphism from A to B. We have a morphism in the local rings, phi inverse of px, bpx, and here we have f x sharp, so this morphism on the stalks, and this is a local morphism. So in fact, actually, by the universal property of the localization, we know that it's unique and it's a local homomorphism. So what this tells us that sorry, we have to show that it's a local homomorphism. So let's see how we see it. So we have this diagram, and from this diagram we get that the so the inverse image under this homomorphism of the maximal ideal in here, so that's just pi x b pi x, that's the maximal ideal in b pi x, and I claim that this is just phi inverse pi x a localized at this prime, and how do we see this? So that would then be the maximal ideal in here, and then we would have that it's a local homomorphism, and we see it simply, so we pull back to B, then we get pi x, we get phi inverse of pi x, and so certainly it's true that so phi inverse of px, a phi inverse of, so this local ring is the same as this pre-image. So just by basically going around here. Okay, so this tells us that we have a local homomorphism, and therefore the pair FFB is a morphism of locally ringed spaces, what we wanted. So we're done with the definition of the functor from rings to affine schemes. Now we want the functor in the other direction. So from the category of affine schemes into rings. And this functor is going to be the global sections functor. So on objects, we just look at the global sections of this sheaf. So this means just, so OX is a sheaf, and we look at the ring when so OX of X. And so we call this the global sections functor. That's what it does on objects. And now let's see what it does on morphisms. So let's take one. FB from XOX to YOY. And now we have to define gamma F. So this goes from gamma Y OY. So actually, so this global sections functor, we don't need to have the structure sheaf here. We could have something different. So it's good to remember this. This functor is used quite often, and probably we'll see it in some later videos again. Okay, so here we have OY of Y, and now we just take our FB and FB with a subscript Y. So it's a morphism of sheaves, and we look at the rings when we plug in Y. So we get, let me write it out, so we get a direct image of OX at Y, and now just by the definition of the direct image, that's just OX of X. Let's check why this is true. So we have OX of the inverse image of Y, but the inverse image of Y is just X. So that's gamma X OX. Okay, so that's just what this functors do. And so that's basically just this FB if we look at it on Y. And now we have the following theorem, namely the functors Spec and gamma define an equivalence of categories. Okay, of course this equivalence is contravariant, because the functors are contravariant, but that's nothing to worry about. So let's see. Let's look at the spectrum functor. It's essentially surjective. That's just by definition, because we defined affine schemes to be the ones which are isomorphic to the spectrum of a ring, so that's immediate. Then gamma, so if we first take the spectrum and then the global section, I claim that this is isomorphic to the identity of rings, so we have a natural transformation between these two functors. Let's see why this is the case. This is also quite easy, so we take spectrum functor, and we've seen that, where did we define it? So basically this node here is what gives us this result, because on the global sections it's just phi again, and then if we take the global sections, well, we get the same map back. So we have that it's on morphism, the identity on rings, this composition. And now what we need is that if we compose it the other way around, that it's on morphisms, the identity on affine schemes. So let's see this. Let's take a morphism from an affine scheme into another affine scheme. And as before, so sometimes we write F, sometimes we write F and FP, but we mean the same thing. And now we set phi to be gamma of F. So if we set phi to be gamma of F, the global section functor of F, then we need that the spectrum of phi, which we abbreviate by A phi, has to be F. So how do we get this? Let's take a point in X, which is spectrum of B. And now let's have a look at the following commutative diagram with A, phi, B. We have A and then pi f of x, so the prime ideal corresponding to f of x, and we have the prime ideal corresponding to x. And then, so actually we can draw it thick, but because we know that we have this map on on the local rings, but I don't draw it thick because actually by the universal property of localization we get that this map is actually unique, so we know it exists because well, we just have this morphism of affine schemes, and it's also unique. We also know that it's local because a morphism of affine schemes is a morphism of locally ringed spaces, which means that the maps on the stalks have to be local. And this tells us that, write it nicer, so pi f of x, and then the maximal ideal, so the local ring here, this is just the pre-image of the maximal ideal on the right hand side. Okay, but this, let's now give names here. Let's call them IA and IB, even though they don't have to be injections. And now we know that pi f of x is just the inverse image under f. So it's the inverse image of this, and now we use this equality, which tells us that it's this inverse image. And now we use the commutative diagram, which tells us that it's the same as phi inverse of I b inverse pi x b pi x, and that's just phi inverse of pi x. And well, what does this tell us? Why did we do this? Well, this tells us immediately that a phi is equal to f as continuous functions. So f of x, so the prime ideal corresponding to f of x is the same as the pre-image under phi of the prime ideal corresponding to x. So that means that these two are equal. And now what we also have is that a phi, and then so this map on the stalks makes the previous diagram commute, and this tells us that a, so let me write it. So we first get this equality at the stalks for all x, but if the maps are equal on the stalks, they are also equal. So also these two maps are equal, and therefore the maps on topological spaces are equal, and also the maps on sheaves, which gives us this. Okay, so we have this equivalence of categories. That's really nice. So we know now that we can work with rings, or we can also work with affine schemes. And actually more holds true. We won't prove this, but let me state it so that you know it. Let's take a locally ringed space and an affine scheme. Let's say y is equal to a spectrum of A, and the claim is that there exists a natural bijection between two Hom sets, namely the Hom in the category of locally ringed spaces from x ox into y oy, and so the bijection is here. The homomorphism of rings from A, so y is the spectrum of A, into the global sections of the structure sheaf on X. And as I mentioned, we won't prove this, but it's helpful to know this. Okay, thanks for watching. Next time we'll probably see a little bit more properties of schemes, and yeah, that's how we'll go on. Thanks for watching, have a good day, and bye.